Welcome everybody. Welcome to Training Machine Learning Models Faster with Dask. We have Scott here, and take it away, Scott.
Thank you. So today I'm going to talk about, as was just said, I'm going to talk about training machine learning models faster with Dask. I'll explain what that means and exactly what's required on these slides. I'm a graduate student at the University of Wisconsin-Madison. I study machine learning. I'm nearly done. It's been 5 years. I'm almost getting out. So that's good. So my history with Dask involves, I worked some with Anaconda back 2 years ago to work on Dask ML's hyperparameter optimization. This is not that. This is completely different. It's similar themes and not quite the same. I'm excited to see where this goes in the future. So today I'm going to talk about 5 things. So I'm going to first mention, I guess, problems with machine learning and why you should care about training machine learning models faster. And then I'm going to explain in internal detail, which at first might not seem important, but it turns out it can have some important user-facing benefits with the right distributed system. And I'll explain exactly what I mean by that. And then I'll show some software I wrote that realizes those benefits. This is joint work with Joe Holtz. He wrote most of the software that you'll see. And I should also mention that that this is an architecture talk. So I'll be mentioning more, I'll be oriented more towards the mathematics. I won't mention so much Dask specific stuff. I'll mention more of the more of the math behind what to implement with Dask. I mean, my software uses Dask and all of that, certainly true. That's certainly true. But I'll be oriented towards architecture in this talk. Okay. So if you fall asleep for the next 20 minutes, there's a couple takeaways. The first takeaway is that I've developed a method, or I haven't really. Other people have developed a method to train machine learning models 2 or 3 times quicker than standard SGD. Standard SGD is, I'm sure, what the data scientists are using. The requirement for this is, so this is not a free lunch. The requirement is that there be a variable number of workers so that the number of workers can change throughout the optimization, or that you have all those workers available initially, but then I'm not really seeing the benefit of my method. So the takeaway is that you need a distributed system like Dask to change the number of workers. Okay. So let's get into machine learning and let's look at some popular training examples. So one very popular training example is with ImageNet. So that's pretty much image classification, identifying objects in the image. So for example, these images all have a barn in them. So in the ImageNet database, which is a very popular data set that has 14 million images, all these images would have the label barn attached to them. Or maybe if you're on Google's "I'm not a robot" prompt and you see crosswalks, that's you identify crosswalks in the image. Well, same thing. They want to detect where the crosswalks are, so when they develop their self-driving car, they know where the crosswalks are. This is pretty much the same data set. One very popular model to use on this data set is ResNet. I've used that a couple of times. It's a deep neural net with millions or billions of parameters. I'm not sure which one. It's large, certainly. And if you look at TensorFlow's TPU example, that requires 17 hours to train to pretty high accuracy on a Google TPU. That's a long time. Another example is with natural language processing. So let's say we want to do well in this data sets. This data set about questions. So it's the choice of plausible alternatives data set. There's like 1,000 questions in this data set, but we want to do well in this data set. So it has questions like, the man broke his toe. What was the cause of that? And obviously was he dropped the hammer on his toe, not that he had a hole in his sock. So we'd like to answer that question with 100% accuracy, or answer the questions like this with 100% accuracy. Natural language processing, NLP, has seen a ton of work in the last 2 years. A lot of progress has been made. One some of that progress is shown with GPT-2. That's OpenAI's model. This was one of the first ones in 2018 that came around. There are some drawbacks though. So mostly it requires an expensive pre-training step, pre-training step, like some feature engineering that takes 1 month on 8 GPUs. That's a lot of time. That's actually a lot of money too. That's like $6,000 if you use Amazon's prices of a GPU costs $1 an hour. That's a large barrier. And then additionally, the training takes pretty much a petaflop day, which if you map out to 4 high-end GPUs, is 2 days of training. That's a long time for training. Again, that's more than 17 hours. That's 48 hours. So I know if I was doing this, I would be debugging this while I was doing this. I would launch the jobs on Amazon EC2 or whatever, somewhere, to do the pre-training, and I realized I made a mistake halfway through and have to hit Control-C and restart the entire thing. That is, I'd be debugging, so I'd have some large supercomputer to do the fitting, to do the model training, the model fitting, and I'd be interfacing with that, and I'd be in a debug loop like that. I like to speed this debug loop up because I have a whole computer to do it. Why can't I just take over the entire supercomputer? That's what I'm asking. And then of course, all right, so then the data scientist workflow is I have a data set in, I do a bunch of debugging to make the model work, and then I produce the end results, the end model. I like to speed this loop up because that's what I use. That's what I spend my day job doing, is in this debug loop. Okay, so now let's go into the specifics of how to speed that loop up. So no surprise, deep learning is required to get the models. So ResNet is a deep learning model, absolutely. The NLP GPT-2 is also a deep learning model. Deep learning is kind of a buzzword. Turns out deep learning really means big data. That big data is required to get these models. So the models can become more complex because they have so much data. So in the case of GPT-2, they use pretty much the entire internet for training data because it's a natural language processing. Turns out the internet's a great place for natural language. And if you look at ImageNet has over 14 million images. And they're not just 28 by 28 or 32 by 32 images. They're full scale images. So it's even more challenging. This is especially challenging in the training process. So the training process requires to approximate the data set with a few examples, because that way we don't have to deal with the entire data set. We can only deal with portions of it. So to see exactly what I mean by that, let's step through a use case of where we have small data and we can use the entire data set, and see how big data is different for the training process. So here we're going to find a model W via some iterative process. Might be SGD, might be ADA, might be ADA-grad, maybe some optimization, some iterative optimization process, which is really all optimization. So I'm going to show, I think, 2 equations in this talk. I'm going to show both of them on this slide. This is the first equation. So this equation only represents how we want to update the model. Just saying that we basically compute some vectors, gradients, GI, and subtract them from the current model. And that's our new iterate. And then we repeat this process many, many times. Here, the bottleneck is the computation of GI. So each computation, one computation, computing GI requires feeding one example to the model, and then evaluating the gradient from that example. And then in this case, we would sum up all, let's say n equals 1,000. We have 1,000 examples in our data set. We would sum up all 1,000 examples and subtract them from the current model. This is the classic gradient descent used in all of optimization literature. Big data is different in that n, the number of examples in our data set, is very, very large. So in the case of ImageNet, n is 14 million, and the combination of 14 million gradients, or 14 million gradients, or evaluating 14 models with backpropagation is infeasible. We can't do it. So instead, by the law of large numbers, we just say, let's use B examples instead of all examples. And hopefully by the law of large numbers, or the central limit theorem, it's close enough to the true value of the sum of the mean, I guess. And so let's just use that instead. Here, B is much smaller than N. So if N is 14 million, maybe B is only, the batch size B is only 512 or 1024. So it makes the model updates feasible, and they can actually run in efficient time. Yeah, so this also, all this really says is that B is static throughout optimization typically, and B is much smaller than N. So the takeaway from that was that the batch size is pretty critical to all the deep learning methods I've seen. Now I want to make sure, so understanding the batch size is pretty critical to the rest of the presentation. What questions do you have? I can't see the chat, so maybe I can.
We don't have any questions right now, Scott.
Okay, that's good. All right, so the rest of this talk will be on how to change the batch size to enable faster optimization. Okay, so first, let's look at how the batch size is specified in pretty much all the deep learning libraries. So the batch size is typically an integer that's common throughout optimization, that's static throughout optimization. So if we look at Keris's MNIST example, they say the batch size is 128, and that's used throughout the entire optimization. This is common, so typically it's some power of 2 between 32 and 1024. This works well with GPUs and all of that. So that's great. And this is common for all of the deep learning libraries. So Keras, Pytorch, TensorFlow, MXNet, Chainer, whatever. It's common for all of them. Okay. So now let's implement these model updates in a distributed system. So as a reminder, we're implementing the equation there on the top with B examples, where B is some power of 2, some small power of 2. And the bottleneck is the computation of this variable G. One evaluation of this G requires feeding one model through the data, or through, excuse me, one example through the model. So one thing you might do with a distributed system is just say that each worker processes, say, a constant number of gradients, say 256. With that, if you had a batch size of 256, you would use one worker. If you had a batch size of 512, you would use 2, 1024 would use 4, and so on. And so naturally, if we do this, we can make the, if we grow the number of workers with the batch size, we can make the model update time agnostic to the batch size, because yeah, there's some communication, but that's not the huge bottleneck. The bottleneck is really the computation, not communication. And so this has been shown empirically too. And that's represented by this graph by Goyle et al. This was, I think Facebook developed this. They trained ImageNet in an hour, and they wrote a whole paper on that, and section 5.5 is relevant here. So what they did was they did exactly this architecture where each worker processes 256 gradients, and they grew the batch size by a factor of 44. So they went from 1 worker to 44 workers, and they found that the model so that's a huge increase in batch size, right? But they found that the model update time only increased by 13%. So it's pretty much agnostic to batch size, right? With 1 worker, or if you were doing this on your own CPU, you'd expect to grow by a factor of 44 naively. But because we did this fancier distributed architecture, we can make the model update time, the time for one model update, agnostic to the batch size. That's a key takeaway. Is with the right distributed system, the right distributed architecture, we can make the time for one model update agnostic to batch size. So keep that in mind when I talk about the next thing. So it turns out, all right, so one method to require fewer model updates is increasing the batch size. So this means changing the batch size throughout optimization. So instead of having a static integer batch size, now we'll have a batch size that depends on the current iteration, maybe the current model, stuff like that. There's a lot of work around this, both theoretical and empirical. The theoretical work says that if you change the batch size in a certain way, you won't require any more model updates than gradient descent, which is a huge feature. The empirical work does something that's not motivated, that's not really founded in theory, but it works really, really well with good models too. So here they show that if they, so the blue line in the graph on the left is if they just decay the learning rate. The red line is if they only increase the batch size, and they see that when they do that, they require like a factor of 3 fewer model updates, which is could mean a factor of 3 fewer training time too, or factor of 3 less training time be reduced by a factor of 3. That's what I'm looking for. Okay. So, so I'm sure the question I had was why is this the case? And this slide might go too in the weeds. If you want to fall asleep for the next minute or so, feel free. But this is motivation for why the batch size should increase, I think, in my view. So basically it's, okay, so let's say we feed one example through the model and we read out the gradient. Let's say we do that again for a second model and read out the gradient again. If we have very poor initialization, the optimal model will be in the same direction for both of those examples. So the gradients will both be very similar. So that's represented by this graph here. I'm trying to minimize, so I'm basically trying to find the mean of the X and Y coordinates for these 4 blue points, or I'm trying to minimize this objective function. So the green diamond is the model, the estimate of the average, and the dashed red lines are the gradients for each example, and the solid line is the mean of all 4 examples. And here we see that all the gradients are pretty similar, so maybe there's not much gain in choosing batch size of 1 versus a batch size of 2, because they're both, all the gradients are pretty similar. The gradients don't change much if we have more examples. If we're very close to the model optimum, all the gradients are very different, but we're trying to minimize this objective function up here. So we care about the mean of examples, and so the mean points says that we're pretty close on the y-axis, but we should go a little to the right on the x-axis. And if you, so I have some formal theorems for this, but basically the gradient becomes more diverse for some measure of gradient diversity as you get closer to optima. This measure of gradient diversity has something to do with orthogonality of the gradients. That's not too important. For full details, you can see this reference to here. Okay. So the main takeaway from that section was that increasing the batch size can yield fewer model updates. So, okay, so the takeaway from the last 4 or 5 slides was if you grow the batch size, you can have fewer model updates. And if you have the right distributed system, the model update time can be agnostic to the batch size. So the question I asked is, if I grow the batch size and have the right distributed system, can I have quicker training? It will take less time to train. The answer is yes. This makes a lot of sense when computation is a scarce resource and you don't want to waste time, scaling up right away, or when you have limited expertise available and you can't really find the right algorithm to figure out how to use. I mean, so you can do this. You can do this with a constant large batch size too, but that takes some more expertise and the right choice of hyperparameters. Scaling up just naively is very simple. Okay. So I've written software to do that. The software runs pretty much this data flow. It says let's train a model for a bit with 256 gradients, or let's say one model update with 200 with a batch size of 256. On the second update, we'll have a batch size of 512, and we'll have twice as many workers. So the batch size and number of workers are linked together. This software uses Dask. So perhaps this slide is, I don't have to describe the slide too much to this audience. It uses Dask, or so works with a variety of clusters, like pretty much anything in Dask Job Queue, Dask Kubernetes, local cluster, whatever. As long as you can change the number of workers, the software works. It also works with Pytorch models, not TensorFlow or Keras. Pytorch is developed by Facebook, and they are a newer software, so they have some nicer features. Things like serialization is a little more mature and a little faster in Pytorch, I think. My software also has a declarative scikit-learn API. That's not too important, but it provides some ease of use for the data scientist. The software has this architecture. It has a centralized parameter server architecture. So there's one worker with the model, and that worker talks to other workers or through the scheduler, I guess. And it sends the models to the workers and gets back the gradients. So in this case, if there were 2 workers, this would be the case when they had a batch size of 512 instead of, so each worker would compute 256 gradients. The model lives on this master node. Every other node is purely functional. So it receives tasks and computes the gradients. There's no state, none of that. Okay, so let's run some experience with the software to see how well it performs. So let's reproduce some of the previous work by Smith et al., the graph I showed previously. So what they showed was that if you increase the batch size, there's no difference in terms of epochs, in terms of number of data through the example, through the model, but there's a huge difference with model updates. So if you increase the batch size, you'll require a lot fewer model updates, and we show the same thing. So to show that, let's use the Sievert 10 dataset, which is an image classification dataset with 32 by 32 color images. Not important. And let's use a wide ResNet model. So this is a model that has, I think a wide res, it requires GPUs, all that, has a ton of parameters. It's a deep learning model, certainly. And then for the batch size increase schedule, let's increase by a factor of 5 every 60 epochs. This is the same schedule that Smith used. And so they also incorporated maximum batch sizes. So when the batch size gets too large, they decay the learning rate instead, which they have some hand-wavy reasoning for doing that. That's also what I do in my experiments. Okay, so the results I'm showing now reproduce the existing work. So, right. So the difference in test accuracy across epochs or number of examples through the model is the same for every method, regardless of maximum batch size. Here, the maximum batch size, if it's 128, the learning rate only decays. If it's 16,000, the batch size increases to 16,000, then the learning rate decays. 16,000 is like, I think 3 or 4, probably 4 increases. If we look at the same graph, but with model updates on the x-axis instead, we see that that the maximum batch size, a larger maximum batch size, helps a lot with reducing the number of model updates. So good, we've reproduced existing work. So the question I asked is, how does that same experiment, how does the number of model updates influence training time? So we can plot the same graph on the top there. The top graph is just number of model updates versus test accuracy. And ideally, the bottom graph, which shows the training time versus test accuracy, should look exactly the same as the graph above. It's a little different. There's some overhead with Dask, but it's similar, certainly. In fact, if you look at the total time so standard SGD requires about 45 or 102 hours of training, 120 minutes approximately. If you look at the minimum, this purple line here, this with the maximum batch size of I think 5120, requires only 45 minutes. And if you plot this graph, if you plot the final training time and the number of model updates required, it looks like a linear line. So just fewer model updates means fewer training. or less training time. I should add a note. This is not with the current architecture. This is a simulation of the expected results of future work. So there's a big qualification to these results. They're not realistic. I have run more realistic simulations, all of that, but these are perhaps representative results. I see. Okay, I'm almost done, so that's good. And so there's a question on, does the parameter strip exist in Dask cluster along with the workers? Yeah, so the client manages all of the communication between the Dask cluster and the workers. It tells the workers what to do. It tells send the model from this worker to every other worker, broadcast. Okay, so I mentioned the architecture was, the current architecture is centralized. So there's one worker with a model, it broadcasts that model to every other worker and says compute the gradients and then receive those gradients back. The client tells the client and the scheduler, the client tells the scheduler how to communicate. The scheduler tells the data flow between the workers. The model lives on one worker and every other worker is purely functional. The architecture that the simulations are run with, the architecture that we should use is with Dask Pytorch DDP, which is a decentralized architecture. So the model lives on every single worker and they only communicate gradients. So this reduces the overhead by a lot, actually, because you're not sending the model all of that. And it scales up pretty well. This is the best place for future work. This will be and so Dask Pytorch DDP will be mentioned in, I think, at 10:30, pretty soon. And yeah. And right, and so the graphs I showed were with the future work. And yeah, the biggest piece I see there are simulations of what it would look like with future work. So those are the gains we should expect with the future work. Yeah. So in conclusion, I have a couple points. First, the future work is really exciting. I'm looking forward to using the decentralized architecture. In addition, there's a couple, I think, 3 other points. Increasing the batch size is an effective method to reduce the number of model updates. The model update time can be proportional to, or the training time can be proportional to the, all right, excuse me. So increasing the batch size is an effective method to reduce the number of model updates. The model update time can be agnostic to the batch size with the right distributed system. So naturally, if we combine those two, we can reduce training time by a factor of 2 to 3. That's all I have. What questions do you have?
Awesome. Thank you, Scott.
You're welcome.
We have another question there, if you'd like to take it.
Can you, there we go. Yeah, so so the first one is are there other batch size update schedules that aren't just 5 times? So yes, you could do that. So for the popular models like neural networks, which are nonlinear and all of that, they're non-convex in particular. The model updates, so 5x every 60 epochs works well empirically. That works really well empirically. There's been some work theoretically that says they should increase like the linear line. So the batch size should just be like proportional to the current iteration, the number of model updates. That doesn't work quite as well as the method that works really well empirically. So there's perhaps more theory that needs to be developed. Does that answer that question? Or guys, any follow-up questions?
I don't think we have follow-up to that one. We do have another question, but
Yeah.
we're also at time. So It will be nice if you could just type in the answer. I'll keep you as a panelist for a while. Just type in the answer and I'll stop recording this session. Thank you
Cool.
so much, Scott.
Yep, thank you.